So what I will be doing today is again go over the problem 1 from the quiz yesterday. And the heading for problem number 1 is, how do we compute derivatives of functions? So what this is all about, given an interval I of real numbers, and of real numbers I say it's a subset of the real numbers, and the function f that is defined for all x out of the interval and takes on value in the real number system. So function f is a function where the input x is a real number and the output y equal to f of x is also a real number. And the function is defined on an interval. And now, if you look at a function like this, so this is my interval I, and here is a function. We would like to say something about the rate of change of this function. So the question is, what is the rate of change of f at a point x? So you fix an x, you go up here, then you have here f of x, now you have a point on the graph. And the question is, by how much does the graph change at this point x f of x? So we take a point P on the graph, and the question is, what is the rate of change of it? Now the answer to this is sometimes easy and sometimes impossible to answer. In the easy cases, it goes as follows. You take the graph, you put the graph in a calculator. One of these calculators is the Desmos calculator, which I sent in several emails. It's an online calculator. And then it is easy to zoom into the graph. So instead of looking at the whole graph, you zoom into the graph. And if you zoom into the graph, you will see the more you zoom in, the more the curvature of the graph goes away. If you zoom into the graph at the point x f of x, you zoom in, you enlarge, you zoom in, you enlarge, you look at it under a microscope, the graph will look like a straight line. This straight line, what you see, is called the tangent line. So there is a line T that touches the graph at the point x f of x. And when you zoom into the graph, there is no difference between the original black graph and the graph of the tangent line. They match each other to the human eye in the neighborhood of the point x f of x. In the slope of that tangent line, we take as a measurement for how much the graph changes at the point. So we look into the graph, So there is again x, there is f of x. But now we zoomed in. So there is the point P. And when you zoom in, the graph here appears like a straight line. The only difference is if here is x, and let's say here is 1 and here is 5. Now the width here of this interval is a tiny interval. Because you zoomed into the graph, so you don't see the full graph anymore. You see only a really, really small piece of the whole graph. And locally, this graph will look like a straight line. So to compute the graph of this straight line, you go now an entity h to the left. So then you go here to x plus h. And you go here up to the graph. Then the height here is f of x plus h. And now you can compute the slope of this line as delta y so that's the difference in the y values, f of x plus h minus f of x, divided by delta x. That's the change in the x value, x plus h minus x over h. Now, this estimate for the slope of the line gets better and better and better the smaller values of h you take. So if you want to compute the derivative of a function, the slope of the tangent line at a point x, you have to be able to compute f of x plus h minus f of x over h delta y over delta x. And you do this for very small values of h. That means you zoom really into the point, and the more you zoom in, the more accurate everything becomes. So that is the conceptual explanation of what is a derivative of a curved line. How do we measure the slope of a curved line? So that is a derivative. That is the rate of change. In section 2.1, we computed the expressions f of x plus h minus f of x over h for certain values of x. So there x was given 1 or 2 or 3. You had a certain number, and then you had to compute the so-called slope of the secant lines. And you computed the slope of the secant lines for different values of h. Then you see a pattern, and then the limit, whatever these numbers approach, if h gets smaller and smaller and smaller, That is then the slope of the tangent line. Okay, that's part one. So now let's do a few examples. And that is now going back to the first question of Elia. Now, if the first thing, this would be part of your portfolio where you write down in your own words what is a derivative. Half a page, 1 page, you open up a textbook, you look on the internet what you find. Yeah? Something that makes sense of you, what you think, how to explain what a derivative is. And now the examples, most of the examples you put in your lecture notes in your portfolio can be homework problems. Okay, example yesterday, we have f of x equal to x squared. So we take the parabola. And we fix a point on the parabola, that is the point 1, 1. And we would like to compute the equation for the tangent line to the graph at this point here. So what I'm talking about, we have now here this line here. This is the tangent line. In the question, in the quiz, problem 1 was, what is an equation for this tangent line? Now, to compute the equation of a tangent line, we have to compute the limit. So we have to compute the slope of the tangent line, which is f prime at 1. So that is the slope of the tangent line. And to compute the slope, if we have here 1, then we take a point to the right, 1 plus h. But this is now wrong. This is correct, but no, it looks like that the h is big, the 1 plus h is really far away from 1. So what I should do is, I should stay closer. So the 1 plus h is really, you know, a tiny fraction of a centimeter of an inch, a tiny, 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 tiny distance away from 1. So I take a point that is very close to 1, but a little bit to the right. That is then the point 1 plus h. So they stay still in the region when you zoom in, where the graph looks like a straight line. So I look at f at 1 plus h minus f at 1. This is then the rate of change of the y values over the rate of change in the x values over h. And I take h as small as possible. In the problem yesterday, h was 0.01 or 0.001. You could take 0.004, 0.0000769. Just take a small h, go a little bit to the right and see what the slope of this red line is that matches the original line if you stay very close to the point. Now, in our case, it is the same because f of x is x squared. So f at 1 plus h is 1 plus h squared minus f at 1 is 1 over h. Now there are two ways to compute it. Now the method from section 2.1 is the most primitive of all methods, that they say just plug in an h that is close to 0. Now if you plug in h equal to 0, then you get 0 divided by 0, because then 1 squared minus 1 over 0 is 0 over 0, which is not defined. So you cannot do this. But you can plug in h equal to 0.1, h equal to 0.01, and h equal to 0.001. So if you plug in h equal to 0.1, then you get 1.1 squared minus 1 over 0.1. And now use a calculator and figure out what is 1.1 squared minus 1 over 0.1. So someone has to turn on the mic and tell me what this number is.
2.1.
And if you do the next one, then you compute 1.01 squared minus 1 divided by 0.01.
$2.01.
And now you see a pattern, and if you do the third one, you plug this in, you get 1.001 squared minus 1 over 0.001. And if you do this in your calculator, you get 2.001. So you see, if h gets smaller and smaller and smaller, it appears that the slopes of the lines get closer and closer and closer to 2. So if you look at this, your conclusion is then that f prime at 1, the slope of the tangent line at the point 1 will be equal to 2. So the only thing we did, we plugged in the point in our formula, x is equal to 1. We compute f of 1 plus h minus f of 1 over h. And we compute this with a calculator to see what the numbers are. We look at the pattern, and that gives us the derivatives. Now, what is the tangent line? So we use the point slope form of a line, which is y minus y0 over x minus x0 equal to m, where y0, x0, where x0, y0 is the point through which the line passes, and m is the slope of the line. So in our case, it is y minus 1 over x minus 1 equal to 2. And if you solve this, you get y equal to 2x minus 1. So there you have to do some algebra. Y minus 1 over x minus 1 equal to 2. You multiply it through, you solve for y. You get y equal to 2x minus 1. So the line T here is what we have here.
I have a question.
Yeah.
I thought the point slope form was y minus y1 equals m times x minus x1.
That is correct. So you call the point x1, y1, I call it x0, y0, yeah? It's the same formula. And then you multiply it through. Or you write it as y equal to y0 plus m times x minus x0. Or you write it as y equal to f of x0 plus f prime of x0 times x minus x0. Or you write it as y equal to f at a plus f prime at a times x minus a. I replace x0 by a. So these are all equivalent ways how you write the equation of a tangent line. All depends on notation, how you call your point. x0, y0, a, f of a. It's all the same. Okay, so this was the section 2.1 way to compute the slope of a tangent line by computing the slope of the secant lines for different values of h. Take h smaller and smaller, see a pattern, and this is how you get the slope of the line, the derivative. Now we do it a slightly more in sections 2.2, 2.3, and 2.5. We do the same thing, but we do it in a slightly more sophisticated way. So let me make here. So the first way to compute a limit is just by plugging in numbers. So we figured out what is the limit of h going to 0 of 1 plus h squared minus 1 over h by just plugging in small values of h on the calculator and see what the pattern is. So again, to compute limit if h going to 0 of 1 plus h squared minus 1 over h, we plugged in small values of h, and we got 2.1, 2.01, 2.001, and so on. So we get a sequence where this responds to h to be 0.1, h to be 0.01, h to be 0.001. And we see a pattern And we see this goes to 2. Huh? So the limit is equal to 2. If h gets smaller and smaller and smaller, if h gets closer and closer and closer to 0, the values here get closer and closer and closer to 2. So it's the limit of these expressions. So that is the most elementary way to compute a limit. Just you take your expression, your algebra expression, and you plug in the numbers that are close and close to your point A, to your limit point. Now, a second way is now algebra. Instead of using the calculator, we use algebra. So this now, we just compute what is this expression. 1 plus h squared is the same as 1 plus 2h plus h squared. So there I use now the formula that 1 plus h squared is nothing else than 1 squared plus 2 times 1 times h plus h squared, the binomial formula. And I do this, which is the same now as the limit if h goes to 0 of 2h plus h squared over h, which is the same as the limit if h goes to 0 of 2 plus h. So instead of using the calculator to compute what 1 plus h squared minus 1 over h is, I use algebra to compute it. It's the same as 2 plus h. If h is 0.1, it is 2.1. If h is equal to 0.01, it is 2.01. And if h is equal to 0.001, the slope of the secant line is 2.001. And now if h goes to 0, the limit is equal to 2. So again, we have computed now the slope of the tangent line, but in this case, instead of using a calculator to compute what these expressions are, we used algebra. And now we are almost done with the problem when we do now the following generalization. So now I just don't want to know what happens at the point 1. I want to know what happens on any point on the curve. So not just for x equal to 1. So whenever we look at the curve y equal to x squared, and I fix any x, and I go up to the curve, at all these points I would like to compute the slope of the tangent line, not for one specific x, but for any x. Then this is the same as the limit if h goes to 0 of f of x plus h minus f of x over h. F is the squaring function, so you always have to square the input. Again, in this expression, if I plug in h equal to 0, I get 0 over 0, which is undefined, undetermined, so this doesn't help. So I have to do something. In this case, I do algebra. And what is the algebra we are doing here? x plus h squared is x squared plus 2xh plus h squared minus x squared over h. The x squares cancels out. Then you get 2x plus h. And if h goes to 0, in this expression, I can plug in h equal to 0. If h gets smaller and smaller and smaller and smaller, 2x plus h becomes 2x. So the slope of the tangent line at the point x, f of x is equal to 2x. If x is equal to 0, then this is my point. What is the slope of the tangent line at the red point? There, the tangent line, when you zoom in, will be a horizontal line. So the slope will be 0. If x is equal to 1, f of x is equal to 1. Two times 1 is equal to 2. So the slope at this point is 2. And if you take x equal to minus 1, then again, the point is again 1. And in this case, the slope will be, in this case, the tangent line goes like this. You have a negative slope. So it's 2 times minus 1, it's minus 2. So that was the main piece of my lecture, and now comes more examples. Instead of doing f of x equal to x squared, you do now the function f of x equal to x to the 3. Instead of doing f of x equal to x squared, you do f of x equal to the square root of x. And instead of doing f of x equal to x squared, you do f of x equal to 1 over x. So it's exactly the same problem. Everything is exactly the same. But wherever I use 1 plus y equal to x squared. You repeat now this whole process for different functions of f. And I will do, over the next few minutes, I will do one more. But let me tell you what the result will be. And why is this the most important exercise of all of Calculus 1? So this is your makeup problem for quiz 1. So you sent me a solution of this, a written solution for this, for these functions, where you take again x equal to 1 and you compute f prime at 1. Now, if you do f prime at 1, then it's a simple problem. Then you do it the way here, where you just plug in numbers and use your calculator to compute it. But it's also the most idiotic way doing it, because you punch numbers into calculators. A far more elegant way doing it is this way here, is the algebra method, that you compute f prime of x for all values of x. And at the end, then you plug in for x equal to 1 and you get your result. And when you do the problem, the result will be the following. If f of x is equal to 1, do you see the graph f of x equal to 1? It's a horizontal line of height 1. F of x equal to 1, the graph is a horizontal line. What is the slope of this line?
Undefined.
What is the slope of a horizontal line?
0.
0. So the derivative of f of x equal to 1 has to be 0. It's a constant function, and the slopes of constant functions is 0. If f of x is equal to x, you see the graph f of x equal to x, y equal to x. What is the slope of this graph?
1.
1. If f of x is equal to x squared, what did we compute? What is the derivative of x squared? It's equal to 2x. If you look at the graph y equal to x squared, and you look at the point on the graph, the slope of the curve at a point is equal to 2x. Now when you do the homework problem into x to the 3, you do the algebra. Do I have time? I don't have time. When you do the algebra, the result should be 3x squared. And when you do the square root of x, which is x to the 1/2, the result should be 1/2 x to the minus 1/2. And when you do 1/x, and you do the algebra and you compute the derivative, the result will be minus 1/x squared. So what this means is, when you do the homework for x to the 3 at the point 1, then it turns out that the derivative at the point 1, 1 is 3x squared or is equal to 3. So in chapter 2, in all these methods, in all these exercises in chapter 2, we learn how to take the limit of f of x plus h minus f of x over h for different functions f. And then in chapter 3, everything what we have learned, we formulate in rules, which are then the rules of differentiation. And this thing here, what we are doing in this problem is called the power rule, that if you have f of x equal to x to the n, it turns out that the derivative is equal to n times x to the n minus 1. In all of chapter 2, you have to learn to understand why this rule is true. And to make you understand it, we use all types of functions, easy functions. And you go through the procedure again and again. And then in chapter 3, we say, looking at all these results, this is how we summarize it. Okay, last minute again, what is the homework problem? What we did here was the problem for f of x equal to x squared. And now you mimic this problem for f of x equal to x to the 3, for f of x equal to square root of x, and for f of x equal to 1/x. You write this up. This write-up serves then that you get full points in the quiz. You have something for your portfolio, and you already proved the power rule of differentiation. Please turn on your mic and ask questions.
So which part do you want us to write down, the pink or the blue with the I and the I2?
Both.
Okay. And at which point do we plug in the x cubed?
Okay, now it's 8:20. So if you want to stay on here, I do the same problem now again for the next 20 minutes for x cubed.
Okay.
But if those of you who have to leave, you leave now. If you want to stay, you stay. I drink a cup of coffee. I'm back in 5 minutes, and then I do the same problem for x cubed, or for the square root. Yeah.
I just have a quick question. What time do we need to send you the makeup quiz work?
What do you think is reasonable? It really doesn't matter. It's a makeup, yeah.
Okay, so just like within like today and tomorrow or something?
As soon as you send it to me, I change the grade in the quiz, yeah.
Okay, thank you.
But I think you are already overloaded, yeah, with doing the problem out of 2.3 and 2.5. On the other hand, if you do it together, this shouldn't take too long. I will do it now for f of x equal to x to the 3. So the only thing is now you have to write down what I do, then you are done with it already. And then you do it for 1/x and the square root of x.
Okay, thank you.
Okay, so those of you who have to leave, please leave. Those of you who want to stay, stay, and I do the extra 3 piece.
Will you be uploading this recording to your YouTube channel?
Yes.
Okay.